Hello everyone, welcome to the course Coherence and Quantum Entanglement by NPTEL. This is week 7, today is 9th March 2024, where we are going to discuss about again some more topics about this course, and I welcome back you again for this discussion session. Today is the week 7. We have already covered more than 50% of this course, and we are moving towards the ending of the second half and most interesting topics at this moment. We will discuss about SPDC. We will discuss about the discussion was already started in the previous class about SPDC and all those things, and I will continue those discussion. We'll solve some problems. I will show you today about 2F imaging, 4F imaging, some simulation I will show you, because somebody has mailed me that he does not understand that 2F imaging, 4F imaging so what I was telling, that if anybody has any problem, then let me know, then I will discuss them. So I will discuss them today also. So first thing, my plan for today is to first discuss about this discuss few questions which are not numerical one, rather some conceptual questions. Then we'll discuss about the SPDC again, whatever we started discussing in the previous class. We'll continue on that, and after that I will discuss about after that I will discuss about few more problems and end up with the imaging systems and all those details. So I will start this course formally within 2 to 3 minutes. Let us wait for a few minutes such that other people also join. So wait for a few minutes. Okay, so let's formally welcome and start this class for today's discussion, week 7 discussion. So, this is Coherence and Quantum Entanglement course and week 7 discussion, where I am Nilakshi Shanapati, your TA. By this time, you all are aware about that thing, and this is a course instructed by Professor Anand Kumar Jha, and these are the problem solving and doubt clearing sessions which runs every Saturday 5 p.m. to 7 p.m. Okay, and this is a Google Meet link you all must have, and with you where you need to join. And also you have your you used to get the problem solving mails, reminder, all of the things to for to get to know or to be aware about these classes. Okay, so and apart from that, as I used to mention in every classes, that we have one Google Drive link where you can get mm, all of the details of this class notes, and the slides and everything whatever I used to use in these classes, you will get them from there. And next one more thing, if anybody of you, or if you like miss this class somehow, then you can always visit to my YouTube channel and check the videos later. All of the videos are uploaded there on a regular basis, mostly by the every Saturday we take the we take this problem solving doubt clearing session, and after that by tonight you should the YouTube video and all of the necessary files will be uploaded in the Google Drive and the YouTube respectively. Okay, so all right. And one more thing is that you have this you have this Google Excel sheet where you can find all of these recorded lectures for both me. There are two discussion sessions. Both are recorded and both you can find from this Excel sheet. For your information, this is just for your information, and you will get it from your spam portal from this course itself. There is a section called problem solving session. There you will be able to get and access it. And anyways, I used to tell you about this drive folder link and the YouTube link every time, so you have all of the accesses. Okay, so let us start today's discussion. So the previously we discussed a lot of things about we already discussed about coherence. What is coherence? We have discussed about nonlinear optics also in the previous class. Now we have discussed lot of the things about the interferometer, interference. We solved a lot of problem with lot of calculation, mathematics, etc., etc. Now we all of them were mostly in the wave mechanics. We are using wave mechanics till now. But from the previous class, from week 5, we have started transition. We have started to do transition from from classical to quantum. That means we are using now the bracket notation. We have introduced the concept of pure state, mixed state, coherent, and how can we get the analogy with the partial coherence, pure all of the things, partial coherence, non incoherence, and all of the things we have already discussed. So today our aim is to do the aim is to solve the problems, as well as I will first discuss these things, then we will go to some other, then we'll go to discuss we'll go with the discussion, then we'll go with the discussion for then we'll go to the discussion for the SPDC, and end up with the then we will solve few more problems, and then we will end up with the some simulation of 2F imaging, 4F imaging. So let's see what are the let's see what are the problems that is written over here, and we will answer one by one of them. Okay, so firstly it is asking what is the difference between pure state and mixed state. So let me give you, I have already written this answer in proper manner, just to give you a proper answer for this, so that you can take it as note, or you can remember it, or you can just revise it, or you can whatever you want to do, you just do that. And then so for that reason I will just give you the proper answer what it should be actually. So if this question is there, that what is the difference between pure state and mixed state, then the answer is like this, The concept of pure and mixed states is very frequently encountered in quantum mechanics, and the classical analog of the pure state in optics is a fully coherent state. The classical analog of the mixed state in optics in a partially coherent field, such as the field of a continuous wave laser. Okay, a system is said to be in pure state if it can be described by a single wave function. This single wave function can be in any arbitrary linear superposition of the eigenfunctions of the system. However, in the linear superposition, all the eigenfunctions have to have a definite phase relationship between them. On the other hand, a mixed state is a statistical mixture of several pure states. Since it is a statistical mixture, it cannot have a wave function representation, and it can only be described through the density matrix formalism. So that is the main difference, and that is what pure state and mixed state is. Okay. Next question, it is asking, what is the difference between a coherent mode and an incoherent mode? Can a coherent mode be a pure state? I hope everybody of you are aware about the answer by now, but let me give you the answer properly. The difference between coherent state and incoherent state is same as the difference between pure state and a mixed state. A coherent state is essentially a pure state, and an incoherent state is essentially a mixed state. More specifically, in a coherent state, the field at different space-time points have a fixed phase relationship between them. However, in an incoherent state, the fields at different space-time points are not completely correlated in their phase. And the second question, if that is asking that is there any relation between the number of modes? Can a coherent mode be a pure state? The answer is yes. A coherent state is indeed a pure state. Now the next question, it is asking what is coherent mode representation of a field and why does one need it? A coherent mode representation of a partially coherent field is a representation of the field in terms of field modes that are completely coherent. Okay, so what it is asking, what is coherent mode representation and why does one need it? Is there any relation between the number of modes in the coherent mode representation of a field and the degree of coherence? So the answer will be first, let me answer the answer first, the answer of the first question first, that a coherent mode representation of a partially coherent field is the representation of the field in terms of field modes that are completely coherent. One needs it because it is relatively much easier to describe the dynamics of several pure states and then add them up than to describe the dynamics of a single incoherent state as it is. Okay, and the diagonalization of a density matrix is the same as finding the coherent mode representation. Okay, so I hope you understand what is the coherent mode representation and how you can do it with the density matrix, and what is why do we need it. Okay, now the second part, there is a definite phase relationship between the number of modes in the coherent mode representation and the degree of coherence, which is that the degree of coherence is inversely proportional to the number of modes in a coherent mode representation. The number of modes will increase, then the degree of coherence will decrease. This is inversely proportional. Okay. Now the next question, question D, it is asking that how many modes are there in the coherent mode representation of a field that is completely coherent? Give an example of such a field. This is very easy question, and I hope with the previous answer you have already assumed that what will be the answer. So the answer will be that there is only one mode. There should only be one mode in the coherent mode representation for a fully coherent field. And what will be the example? The example is a monochromatic plane wave field. Another example can be pulsed laser field in which all the frequency component have been phase locked. And these things we have already seen that how it is fully coherent field, how CW is not that. So those things we have also calculated with the mathematics and calculations and problems previously. Now the next question E, it is asking how many modes are there in the coherent mode representation of a field that is completely incoherent. Give an example of such a field. For a completely incoherent field, the number of modes is equal to the dimensionality of the basis. Okay. For example, in the momentum basis, a completely incoherent field will have infinite number of modes, while in a polarization basis the number of modes will be 2. So these are the examples. So these are the 5 questions through which we get to know about what is pure state, what is mixed state, what are coherent mode and what are incoherent mode. Can a coherent mode be a pure state? What is coherent mode representation of incoherent mode? How the number of modes is related with the degree of coherence? What are the example of completely coherent mode, completely incoherent mode? All of those things we have discussed. Now we'll discuss about SPD. We'll go back to the SPDC thing and we'll discuss about that. But before that, let us take 2-minute break and then we'll start. Okay, so let us start discussing about the spontaneous parametric down conversion. This is what I have shown here in this slide is nothing but a pump is going and signal and idler is forming, and pump and that is again shown with this schematic diagram in the B, where laser is coming from the laser pump is coming of about 405 nanometer, and two lights are going, signal and idler, and those are falling on the detectors. Already the mathematics of the spontaneous parametric down conversion is shown and discussed in great detail in your lectures, so I will not go to the lecture. I will not go and discuss about the mathematics at this moment, because those you are already aware about, but we will discuss it in more details. And I have already introduced about the spontaneous parametric down conversion in the previous class, where I saw all of these pictures and try to motivate you for all of for this entanglement in various degree of freedom, and shown you that how it happens also with some mathematics. But today I will discuss about it in great details. Please be very careful about the discussion. Okay, so the thing is, let me go. Okay, so yeah, so spontaneous parametric down conversion is the most widely used process for generating photon pairs, photon entangled photon pairs in various degree of freedom, whatever, such as polarization, time energy, position transverse momentum, and angle orbital angular momentum. In SPDC, a pump photon interacts with a nonlinear crystal and splits into two entangled photons, which are called the signal and idler. The SPDC process has been studied very extensively in last few decades with various form of pump and crystal configuration. And the entangled photon pairs produced by SPDC have been used in numerous experimental studies in quantum entanglement and entanglement-based real-world quantum information applications. So now we will discuss about the phase matching of BBO crystal, like beta barium borate crystal, for spontaneous parametric down conversion, and thereby we will also tell about the generation of entangled photons in such kind of crystal. So for that we will discuss detail of the effects of due to the various crystal pump parameters, including the length of the crystal, angle between the optic axis and pump propagation direction, the pump incidence angle on the crystal, the refraction at the crystal surface, and the pump propagation direction inside this crystal. So all of these are the parameters with which this generation of entanglement depends on. And these effects are extremely relevant for experimental situations. So we can we will discuss and show you the numerical simulation also. Okay, so as we were discussing about the spontaneous parametric down conversion. So it is a second order nonlinear optical process in which a photon of higher frequency passes through an optical material and splits into two photons of lower frequency. Okay, and the photon at the higher frequency is referred to as pump photon, whereas the produced two photons are lower, or the lower frequencies are called the signal and idler photon, that you are already aware about. So there are all those discussion is done in the previous class as well as in your lecture. Now we will discuss about something more, which I just told as like parameter with which it depends upon. Okay, so for that what we did, I am giving you a reminder that we first derive the SPDC Hamiltonian and we work out the two photon state produced by the SPDC. Now we study how different pump and crystal parameters affect the phase matching and thus the generation of the signal and idler photons in SPDC. This will include the effect due to several experimental factors, such as like crystal length, angle between optic axis and beam propagation direction, pump incidence angle on the crystal surface, refraction at the crystal surface, pump propagation inside the crystal, and the location of the beam waist of a Gaussian pump field. All these effects are extremely relevant in all of the experimental situation. Okay. We also need to know that what is the probability of down converted protons are both type 1 and type 2 phase matching conditions, like what is type 1 phase matching, what is type 2 phase matching, what is collinear phase matching, what is non-collinear phase matching. So we'll show you that also. So first, for the spontaneous parametric down conversion, we write the what we do is that we write the Hamiltonian, and after writing the Hamiltonian, we propagate it through the Schrodinger picture. We use the we use the second quantization and write the electric field in terms of a dagger, that means the ladder operator, and then we do all of this calculation and end up with the state, which is mostly written as psi tp. Okay, now we have our psi tp, that is a 2 photon state. Then we need to study the effects due to several things. Now in between that, let me tell what is type 1 type 2 phase matching and what is collinear non-collinear phase matching. So collinear and non-collinear phase matching are that when the two signal and idler have the they are collinear in their momentum, like they are signal and idler propagating in the same direction, so opposite direction just of the pump, and in the then we call that state as this Ks and Ki and Kp are not opposite in the same direction. Then we call it as collinear state, and where if it is they are not exactly similar but they form a vectorial, with the vector they conserve the amplitude, conserve the direction and amplitude, whereas they are moving towards different direction, then what it is called is type what it is called is a nonlinear phase matching. And if the signal and idler have two different polarization state, then we call it as type 2 polarization, and if they have the same polarization state, then we call it type 1. I mean, same polarization means type 1 and different polarization means type 2 SPDC. Okay. Now we will talk about the material first. Like this is SPDC, we are talking about that BBO, we are using the BBO crystal, which is beta borium borate. But this is not the only one crystal, there can be other crystals also, like lithium niobate, potassium dihydroid, hydrogen phosphate, that is KDP, also ATP, also PPKTP, many things. And we mostly what we use in our lab is BBO, and every different crystal has their own advantages and disadvantages. What if for the bulk crystal like BBO, we do not have very high down conversion efficiency. Therefore, most in the recent years, like nowadays, periodically poled quasi-phase matched waveguide crystals are being used to achieve higher SPDC efficiency, although they have a restricted phase matching range. Several experiments are nowadays reported by using the periodically poured titanyl phosphate, that is PPKTP, waveguide crystal, and the other quasi-phase matched waveguide crystal that are being used for SPDC in the SPDC generation include the periodically poured lithium niobate, that is PPLN, also periodically poured lithium tantalate. In the past, most of the foundational experiments as well as the experiments exploring the applications in the photonic entanglement have used mostly BBO crystal for producing entangled photon by SPDC. Now, the more recent experimental studies that require high down conversion. 1 minute. Yes, 1 minute. That requires more high down conversion efficiencies in limited the more recent experimental studies that require the high down conversion efficiencies in limited emission directions have started using the quasi phase match periodically poured crystals for the purpose. So, either foundational or application oriented that do not necessarily require very high down conversion efficiency, and we can still employ BBO crystal because of its own advantages. This is due to the fact that the quasi phase matching process that enables the periodically pulled crystal to have high down conversion efficiencies compared to the bulk crystal does so at the expense of limiting the phase matching ranges. As a consequence, although the periodically folded crystal become highly efficient for collinear down conversion, the quasi-phase matching in such crystal does not allow for non-collinear down conversion. For that reason, while these crystals can be used for studying temporal and correlation of entangled photons, they are not effective in studying the spatial correlation of entangled photons in nonlinear emission geometry. The phase matching in the periodically pulled crystals is achieved by changing the temperature of the crystals, and therefore these crystals require more temperature tuning also. And the stability for achieving the desired phase matching condition also is very not like temperature variable, and temperature variation is there, and we did not more lot more precautions. On the other hand, in case of BBO crystal, broad phase matching ranges can be very easily achieved. Not very easy, but easily achieved. Both the collinear and non-collinear phase matching requirement can be satisfied simply by changing the angle between the optic axis of the crystal and palm propagation direction. And for that, we just only use a goniometer. That's all. And moreover, these crystals have broad transmission ranges, have high damage threshold, and are readily available with various thickness. Therefore, a substantial number of experiments, especially those in the spatial correlation of entangled photon, still employ BBO crystal for generating entangled photons via SPDC. Now, as I was discussing, we know how to what is the Hamiltonian for SPDC, and how to do the Schrodinger picture, use the Schrodinger picture to get the two photon state. Finally, all of those are already shown in your lectures. I will not go into the detail of that, of course. Then we arrived to that for to the psi TP, that is the two photon state. And here in this picture, as I forgot to mention, but you guys have must have understood that this is showing that laser is coming, pump is going through the crystal and producing signal and idler, and this is the optics axis of the crystal, as it is a birefringent material. And then this is the of L thickness, and say this signal and idler going, where the pump is also passing through it. And for that, experimentally, to block this pump, we actually use the use a bandpass filter. Okay, all right. Now, what are the effects that we see? First of all, the effects due to the beam waist location of a Gaussian palm beam. In most of the situation, what happens that the palm field is taken to be in the form of Gaussian beam, and the location of the Gaussian beam waist is taken to coincide with that of crystal. In many experimental situations, the location of the palm beam waist does not coincide with that of the crystal. Effects of this kind have been studied in various papers, and we need to know that what we need to do is that we need to first take care of this thing, and we need to do some modification in our equations for considering the beam waist location. So this is the first effect. Second effect is the effect due to the non-normal incidence of palm field on the SPDC crystal. How is that? It is quite often that the case that the SPDC crystal is oriented in such a way that the palm field is incident on the crystal at an angle other than 90 degree. So in this case we have some effect, and that also need to be taken care of. And for that we consider the effect on the two photon coincident count rate caused by the non-normal incidence. And the SPDC crystal is rotated by an angle alpha with respect to the pump propagation direction. Inside the crystal, what it is showing over here, let me go to the next slide. Maybe it is not I have not shown it here, otherwise I could have discussion, but okay, all right. So but the thing is that what I need to mention is that the non-normal incidence need to be taken care of, and for that we have angle we consider an angle which we consider and do the modification according to that, such that we can use this non-normal incident angle as a parameter. Now we need to note that the palm field polarization is decided by the phase matching conditions, and we know that the phase matching considerations that the palm field has the extraordinary polarization, like for the BBO crystal, the what I can say, phase matching considerations that the palm field has to be extraordinarily polarized for negative uniaxial crystal such as BBO. So that you need to taken care of. So that is one more requirement. Okay. So first requirement was first requirement which you need to consider of that effect of the beam effect due to the beam waist location of a Gaussian pump. Second is that non-normal incidence of pump field on the SPDC crystal. Also the state of polarization of the pump. These three things. Now polarization effects in pump in SPDC is a huge thing. It itself it was a very it was studied in very detailed manner in several papers. Okay. So you can find there are textbooks also. In the textbooks like Robert Boyd books, Mandelwolf, and Loudon, all of these books also have their many details given in those books also. Now for the BBO crystal, as I mentioned, this is a negative uniaxial crystal, so you need to have the pump of extraordinary polarized light, and and if it is a type 1 crystal, then it will produce two orthogonal polarized two ordinary polarized light. Whereas the type 2 BBO crystal, if you send the extraordinary polarized light, then it will give you one signal as extraordinary, idler as ordinary, or signal as ordinary, idler as extraordinary. So that is type 2 BBO crystal. So there can be two type of BBO crystal. Okay. And I have already mentioned that when both the signal and idler have the same polarization, it is referred to as a type 1 phase matching, and when they have orthogonal polarizations, then it is referred to as a type 2 phase matching. And this BBO is a negative uniaxial crystal. Now you need to consider the wave propagation inside the SPDC crystal, which is a nonlinear crystal, and you need to do all of the you need to take care of all of these, that how the refractive index is varying, how they are changing, and how we need to consider, and we also need to consider them in case of our study. So those are the very details I am telling all of these just to make you understand that generate entanglement through this SPDC process experimentally is not that is easy, but not that easy. You need to take care of lots of parameters. And here in this figure, in this next figure, you can see it is showing that laser is coming, and it is passing through, and it is going where this is the omega W0, that is the beam waste at beam waste, and we know that when laser light propagates, it form a Gaussian light, and whereas it has a W0 beam waste, and this is the beam waste plane, and from that it is propagating d distance, and this is a crystal which has L length, or L thickness, and after passing through it, it is producing signal and idler, but in the all directions. So ultimately what you will observe in your plane, in your image, in your observing plane, that is a ring, because this is a this will be a three-dimensional thing, right? So for and based on that, if you plot your state and get the then you will be able to see the SPDC ring. Like these are DEF is showing the numerical results, whereas this ABC is showing the ABC is showing the proper experimental results that we have in our lab that we produced in our lab. So these are the things, and we actually had a have a app also to check these SPDC conditions, to play with the SPDC parameters, to get to see that how the SPDC observe how it is varying, like with alpha beta. There are several parameters that you have seen in your lectures, like if we change them, then how it is changing in the how the SPDC ring changes. So that is certainly that is I found that at this moment is down, that app, so I cannot show you. I'll try to show you in the next class. Okay, so as I was discussing about the SPDC for long enough time, So yes, let me continue on that. It can the theta p I was talking about. Theta p is the difference angle between that optic axis of uh, op, the difference in the optic axis for the normal coincidence, and and the non-normal coincidence. And you have already seen in your lectures that what is theta p look like in the if you draw it schematically. So that's why I am not discussing theta p in very detail. But I am not showing the theta p. But the next topic which I am going to tell you, that apart from all of the things that I have already mentioned that SPDC depends on, the next thing with which this intensity of the SPDC depends is the theta p. And we observed that that the photons have maximum intensity in the collinear emission geometry, and as the phase matching becomes more and more non-collinear, the intensity becomes lesser. And this result shows that the intensity and thus the photon emission efficiency is higher in collinear phase matching compared to the non-collinear phase matching. And in experiment in which more intense photon source is required for the collinear phase matching should be preferred. Okay. And last but not the least, I this is although not the last one, but one of the main factor is there, which is effect of crystal length on the down conversion. And the length of the crystal which is shown with the capital L here, that directly affects that directly affects the phase matching in SPDC. Here the down conversion intensity pattern for it is shown for three different values. Okay, one is three different values of the crystal thickness. 1 minute. Here what you see, that I have shown for different theta p value, but we can also plot the same thing for different L value, that is a different thickness, that unfortunately I have not shown here, but that can also be done. So, and that is one of the one other parameter with which the ring can be varied. So however it does affect the width of the annulus, which become broader as L becomes thinner. That means smaller the width of the thickness of the crystal will have larger annulus of the SPDC ring. Okay, this means that as the crystal becomes thinner, the phase matching becomes more relaxed, it becomes more prominent. And that can you also see with the functions, that is already, functions in mathematical functions, and you can plot it in your Python or Mathematica. You can try it by yourself, because all of these equations were shown in the lecture. I am just discussing the SPDC in much more detail. Because you can get small questions from in your NSEM or some other quizzes, where they can ask that how the SPDC changes, SPDC ring and SPDC can be affected by various real life parameters in case of experiment, and all of these parameters need to be considered when you are working with SPDC or entangled photon generation. So all that is very easy, but it is not so easy. Okay, so so after that, and I have discussed most of the parameters, but I am thinking that if I have missed any of them, I think no. And if you again, I will mention that if you miss the previous part of this discussion, then you please go to the YouTube channel. There you will find this discussion session video after by tonight today midnight or something like that. Okay, so I was discussing I have discussed few questions answers in the very beginning, and then I was discussing SPDC for a long time. Now I will conclude the SPDC thing. Okay, so SPDC is is the, again I am saying, SPDC is the most widely used process for generating photon pairs entangled in various degrees of freedom, like entangled photon pairs in various degree of freedom, such as position momentum, energy time, polarization, and orbital angular momentum. In SPDC, a pump photon interacts with a nonlinear optical crystal and splits into two entangled photons called the signal and idler photons. The SPDC process has been studied extensively in the past few decades. It's about like it is more than 50 years now. I think not 50. I exactly not remember, but past few decades with the various uh, pump and various crystal configurations. And the photon pairs produced by SPDC have been used in numerous experimental studies on quantum entanglement and entanglement based real world quantum information applications. That's why this is so important to us in this course, that I discussed at the end of previous class also with this SPDC process, and also today about 40 minutes I am discussing about this SPDC. Okay, so we have here presented a thorough study of phase matching in the BBO crystal in today's discussion, and also studied the entangled photon generation by SPDC. We have discussed in details the effect of phase matching due to various crystal and pump parameters such as length of the crystal, angle between the optic axis of the crystal, and the pump propagation direction, the pump incidence angle on the crystal surface, the refraction of the crystal surface, and the pump propagation direction inside the crystal. You have also seen all of these things in your lecture, but I discussed it again just to give the focus on this process. And we have also presented the theoretical and experimental results in this slide, which is illustrating how various phase matching conditions affect the generation of photon pairs by SPDC. Okay, so this is the thing that I wanted to discuss and convey to you. And after that I will go to this go and to this just I'll discuss about this two photon interference effect in uh, very first, and then we'll solve some problem, and then I have the plan to show you the uh, imaging conditions and the Fresnel diffraction, what is 2f imaging, 4f imaging. I have done the simulations of them also. I'll show you, and I'll help you to understand that how you can also simulate anything like that. But that if time permits, then I will do them today. But for now I am talking for more about 1 hour, so let us take 2 to 3 minutes break, then I will start again with the two photon interference. Okay, so let us have a 2 minute break. My throat is now paining. Okay, so let us have 2 minutes break. I will discuss about the two photon interference with after 2 minutes. Okay, in this slide, you see that there is like this setup which is showing that light is coming, the pump is coming and falling on this PTC uh, parametric down conversion to second order nonlinear crystal, and passing through it there are signal and idler is creating, and there is one, of course, another mirror, and it is again passing through this PTC. This when passing through this first time, it may create signal and idler and may not create. When it is again coming backward, then it can again create signal idler or not. So based on that it can have two two certain conditions. Either this pump is coming and generating signal idler and we are getting coincidence, and second thing is that pump is coming, it is going backward and we are getting backward this signal idler, and they are again passing through it and then we are getting coincidence. For this first thing, we will have lesser time to detect the signal idler. For the second one, we will have much more time, we will require much more time. So this setup is called a double pass setup, through which we can actually do the coincidence measurement. That means that the photon signal is falling on this DES detector at time t, and the idler is falling on a detector DI within the time t plus tau, where tau is in very small time scale, that is some 1.5 nanosecond or something like that. If that happens, then what we have, that two simultaneous measurement through the detectors, which we called as coincidence, that is nothing but the interference of two photon state, and this is what we call two photon interference. We know about the one photon interference. Now we will study the two photon interference and many more interesting effects with the entangled photon. So, so we know how to produce the entangled state and also what are the relevant quantities for detecting it. We'll now attempt to describe two photon interference. By that, we'll try to explore the two photon coherence. In case of one photon, let us as we have done in case of one photon, we'll do the same in case of two photon interference in the temporal domain. We'll try to describe two photon interference experiment using the same situation of the one photon interference, and that you have already seen in your lectures. Now I will show this with the slides and not I'll not describe the line by line mathematics now, because now you need to just get a whole idea and then we'll solve the problem. Two photon interference effects are observed with the entangled two photon fields, and they can be described as a two photon interfere with itself, told by Dirac himself. Okay, so this is a two photon state which is interfering with itself. Okay, and we will get to see the interference, which is called as two photon interference. In terms of coherence, one can say that two photon interference occurs as long as the two photon alternatives are coherent with each other. And for that reason, in the next slide you can see this is again shown with here I show the generation of this signal and idler through SPDC with this two-dimensional schematic diagram. Here it is also showing the same for two alternatives. This for the first alternative this is 1, and for the second alternative it is 2. And I'm extremely sorry, this should be 1 and this should be 2 should be the longer time taking path, and 1 should be the shorter time taking path. I have mismatched the 1 and 2, but please bear with me. You can understand that one of them which are taking longer time, that is 2, and which is taking shorter time, that is 1, which is vice versa of whatever I have presented here. Now we can do this path diagram and calculate delta L dash and delta phi, which is the difference between the two path length of two photon state, and delta L dash, the difference between the delta L dash is the difference between signal idler in a path itself, whereas delta phi is the phase difference between the two photon paths. So we can write these things like this, and this is again described in the lecture. So I am just giving you the reminder of these things. So once you can write this, you can find the RSI, that is a coincidence of signal idler, which is itself the interference of two photon state, that as R1 plus R2 plus 2 root over of R1 R2 gamma delta L gamma dash delta L dash cos K0 delta L plus KD0 delta L dash delta phi, where L del L del dash and del phi are like this. K0 is a pump, wave vector of the pump, and KD0 is the pump the KD0 is the wave vector of the pump of the difference of signal and idler field. So the based, and where this gamma delta L and gamma delta L dash are the Gaussian function can be considered like this. This formula you will require various times for your quizzes and exam. So in a two photon interference experiment, the two photon field is made to go through two alternative pathways. The fields in the two alternative pathways are then combined, and the interference is observed in the coincidence count rate of two detectors. We began the representation of a general two photon two alternative interference experiment in the two photon path diagrams which you just saw. Then we consider only the polarization independent temporal two photon interference effects, assuming perfect spatial coherence. Then we also assume the frequency bandwidth of the pump field is much smaller than the signal and idler field. Then alternative 1 and 2 are the two pathways by which a pump photon is down converted, and down converted signal and idler photons are detected in coincidence at single photon detectors, which are DS and DI. For the single photon detectors, we use EMCCD as the detector, which is called the electron multiplying charge coupled detector. It worth about 40 lakh. Okay, so this can be realized, and we used to do this kind of setup and study regularly in our lab. Now two photon interference is observed in the coincidence count rate of detector DS and DI as long as two alternatives are coherent, that is indistinguishable from each other. We here adopt the convention that a signal photon is the one that reaches detector DS, and the idler photon is one that reaches detector DI. In this two photon interference experiment, these alternative pathways can be introduced by using beam splitter, also by passing the pump twice through by using beam splitter, or by passing the pump beam twice through a crystal, which I have shown here, which is called the double pass setup. Or even you can use two different crystal also. So there are various ways, and all of these are already published work. And in here the small l denotes the optical path length traveled by a photon, and phi stands for phases other than the dynamic phase, such as the phase acquired due to the reflection, geometric phase, etc. So you all know about these things, but again I mention that LS1 denotes the path length traveled by the signal photon. In alternative 1, for every optical path length traveled, the corresponding time elapsed is denoted by tau L by C, that you know the distance by velocity, and velocity of the light is considered at C, that is the velocity of light in the free space. Thus, the tau is equal to L by C, and tau S1 represents the time taken in traveling the distance LS1. Various path lengths and phases are used to define in the two photon path length parameters and one phase parameter, which is written as delta L dash and delta phi. Okay. Now in case of a particular alternative, the two photon path length is defined to be the mean of the optical path length traveled by the signal and idler photons added to the optical path length traveled by the pump photon. That is what it is mentioned in the del L and del L dash. The two photon path asymmetry length is defined to be the difference of the optical path lengths traveled by the signal and idler photons, which is delta L whereas the delta L is the difference of the two photon path lengths L1 L2, whereas the delta L dash is the difference of the two photon path asymmetry. That means delta L is the two photon path difference and delta L is the two photon path asymmetry. Based on that, the parameters are these two along with the delta phi, with which we can vary the coincidence, and coincidence looks like something like this RSI, which I have shown in this slide. So this was the story of two photon interference. Now in the week 7 I found that the problems that those which are actually given in your quizzes are mostly polarization degree of freedom. So I will discuss few polarization degree of freedom problem uh, that you can solve, that will help you to solve your assignment problems. And then we'll do one more problem which is related to this interference, and then we will go to the simulation part. Today's main two problems which you need to focus on are problem 2 and problem 3. But before that, let us take again 2-minute break and we'll do the problem 2 and problem 3. So let us solve the problem problem 2 and problem 1 and problem problem 2 and problem 3. So it is saying that so that a general polarization matrix J can be uniquely expressed as a sum of two matrices, one of which is completely polarized and the other one is completely unpolarized. Okay. So the completely unpolarized matrix can be written as, I hope you can see it. Let me unpin pin this. Okay, yes. So J unpolarized can be written as A1001. How? Because if you calculate the degree of coherence or degree of polarization P of this with the formula 1 by 1 minus 4 of determinant of J by trace of J square whole to the power half and all of these things, then what you will get is 0 for this matrix, which is written as J unpolarized. So a general unpolarized matrix can be written as something like this, and a general polarized matrix can be written like this. Okay, where A greater than equal to 0, B greater than equal to 0, C greater than equal to 0. Also BC minus D star is equal to 0. This you need to know. Maybe you can get some question as an option, like multiple choice question, that this is true, and this is something like that. Now we need to prove that J is equal to J polarized plus J unpolarized. Okay, which is a unique decomposition. Now we can write a general J as JXX, JXY, JYX, JYY. Equating left hand side and the right hand side, maybe I can write it like something like this now. A plus B D star A plus C is equal to JXX, JXY, JYX, JYY. Now equating both sides, then we will get A plus B equal to JXX, A plus C equal to JYY, D equal to JXY, D star equal to JYX. Now this is one of the condition. So substitute B and C from the above condition. So D is this, D star is this. From these we can find B and C. B is nothing but JXX minus A and C is JYY minus A. Now BC minus D star equal to 0. That means JXX minus A, JYY minus A minus JXY, JYX equal to 0. Now you need to solve the equation. Solve this, for which you will get two values of A, because you will get something like alpha A square plus beta A plus gamma equal to 0. This will be in this form. And if you use the Sridhar Acharya's formula and all of those things, then you will get two values of A. One I am writing as A1, which will be in terms, I have already calculated and written. The steps I am not showing here, such that you guys do it by yourself the in between steps and practice these things, because I am pretty sure you will get few questions from this problem solving session itself. So this is one, and another is trace of j square minus 4 determinant of j by 2. So these are the two solutions of A, which are the eigenvalues of matrix J. Two solutions of A, which are the eigenvalues of J. Now let us take one of the solution. Any one you can take. Let us take A2. Then B is equal to jxx minus A2, or you can do any one of them, jxx minus A1. That's true, right? This is from this equation. So for the first case 1 and case 2, for 1 b equal to jxx minus A2, if we do, then what we will get is 2jxx minus trace of j plus root over of trace of j square minus 4 determinant of j. What are trace and what are determinant, that you know, let me write for you once. That means you will get in terms of this jxx jyy. Now I am writing them in terms of trace and determinant, whereas determinant of j means jxx jyy minus jxy jyx. So if you get this like this or this, then you will write it as trace of j or determinant of j. Okay. Now this is greater than equal to 0, or in case of 2, b equal to 2jxx minus, or maybe I can write another step such that you can understand that it will be greater than 0, that jxx minus jyy plus root over of jxx minus jyy square minus 4jxy square. How am I writing this? I am writing this was in terms of trace and determinant, and this is the in terms of after substituting this jxx yy stuffs. So this will be always greater than equal to 0. Similarly, if you substitute A1, then you will get 2jxx trace of j minus trace of j square minus 4 of determinant of j by 2. Again, that can be written as jxx minus jyy minus jxx minus jyy square plus 4jxy square by 2, which will be less than equal to 0. So what is the thing? Here b is positive, here b is negative. Again, c can also be positive, c can also be negative from this equation. That means for a valid solution, the term b and c need to be, but for the valid solution, you need the term b and c to be positive. So equal to A2 is only the valid solution. Why it should be positive? Because BC minus DD star equal to 0. And if B and C itself are negative, sum of one of them, then it will not be able to consider, it will not be able to follow the condition of BC minus DT star equal to 0. That's why we need to have, for the valid solution, B and C should be positive for valid solution. So A equal to A2 is the valid solution. That means we can only have one eigenvalue, other one is not true. So A can be only one value, like it. So what we can write? We can write now only A2 1 0 0 1 for the unpolarized, and for the polarized also A2 D star, and C means sorry, 1 minute, B and C means again that will be in terms of JYY, that means that will be in terms of here B is this, and that will be again C2. So A2 and C2, that means only one matrix we can form. We cannot form a matrix which will be A1 D star A C1, and both of them simultaneously we cannot form. We can only have this matrix, not this one, because of the condition of BC minus DT star equal to 0. That means we can have only one unique decomposition. And from that we can say that a general polarization matrix can be uniquely expressed as a sum of two matrices, one of which is J polarized and one of which is unpolarized. Okay, and now the problem B is saying the polarization matrix J of a field is given as J equal to 1 by 8 5 root 3 root 3 3. Write down J as a sum of two matrices, one of which is completely polarized and the other one is completely unpolarized. The part A was a generalized version of this part B only. I always used to show the generalized question such that you can use the similar tricks in your specific question. This has also happened in case of your various interferometry questions also previously. So now I'll show one specific question B for you, such that you can understand that how you can utilize the informations of A in case of B. So read the question once again, that the polarization matrix J of a field is given as J is equal to 1 by 8 5 root 3 root 3 3. Write down J as a sum of two matrices, one of which is completely polarized and other is unpolarized. So let us do that. Let the weightage of polarization matrix is P, and that means 1 minus P will be the J unpolarized. And if we can write this as J polarized plus 1 minus P unpolarized as half 1 0 0 1. Half is the normalization factor. Okay. Now calculate the P. You need to find the P. If you find the P, you know what is this. For that, what we need to do? We need to use that same formula that I was telling just before some time ago. Okay. Now for the polarization matrix, for the polarization matrix, always the trace need to be conserved such that the energy is conserved, and for that trace of J will always be equal to 1. So this will become 4 into determinant of, that will be equal to 1, and you can also calculate the trace of J from here, that is 5 by 8 by 3 by 8, which is equal to 1. So for determinant of J, half Now determinant is 12 by 16. How? Let me maybe calculate. 5 in 5 by 3, 5 by 8 into 3 by 8 minus root 3 by 8, root 3 by 8 whole to the power half. That means 1 minus 12 by 16 whole to the power half, which is equal to half. That means p equal to half. And now now from the equation, this is the equation 1. So now we know that j equal to p into j polarized plus 1 minus p into half 0 0 half. We can write this as p j polarized equal to j minus 1 minus p half 0 0 half, which is again equal to half j polarized, because we know that p equal to half, that we have calculated just now. Then 5 by 8 root 3 by 8 root 3 by 8 3 by 8 minus 2 by 8 0 0 2 by 8, because substitute 1 minus p equal to half, sorry, will be 8 or 4. Whatever, I mean, you can calculate, it will be 4, I think, or we can write it in terms of something like as we are writing in terms of 2 by 8, that's why it is like 1 by 4, that means equal to 2 by 8. This will be 1 by 4, that's why we have written 2 by 8. I mean, I have previously written it in my notebook such that just for simplification of the calculation. Then what we will get is just simply do the matrix division, matrix difference, matrix difference, then it will be nothing but this. So this is the half into j polarized. So j polarized will be 3 by 4 root 3 by 4 root 3 by 4 1 by 4. So we can write the j as p into j pole minus plus 1 minus p into j unpole, that means polarized and unpolarized, that is equal to half into 3 by 4 root 3 by 4 root 3 by 4 1 by 4 plus half into half 0 0 half. So we have successfully decomposed the matrix into in terms of polarized and unpolarized matrix, and this is nothing but the coherent mode representation of a incoherent matrix. Okay, so this is the problem 2, and now the problem 3. Let us try problem 3 by yourself, or let us just you just actually go through the problem 2 once to understand it by yourself, and take yourself 1 minute time, and then I will come back with the problem 3, otherwise it will become so fast. So let us wait for 1 minute and we will do the problem 3 now. Okay, so let us start discussing the next problem, which is saying a polarization matrix can be expanded as a linear combination of identity matrix and the three Pauli matrices which are J, which is J equal to, which can be written as like J equal to half summation of I Si sigma I, where S is called the Stokes parameters and sigma is called the Pauli matrices, where sigma 0, sigma 1, sigma 2, sigma 3 are given to you. If you are not aware about the Stokes parameters, here you do, although you do not require, then please go and go to the Stokes, go and read what is Stokes parameter. Okay. So now the next question, the question it is asking, problem A, is that first of all, so that for a general polarization density matrix, determinant of J is greater than equal to 0. So let us do so. Let us see how I can do it. This is a general J matrix. General J matrix means general polarization matrix. This is our notation. We always use J for a general polarization matrix. Now Jxy okay, so determinant of J will always be like, how can I tell? Determinant of J will always be equal to greater than equal to 0. If it becomes equal to 0, then it is a unpolarized matrix. Like this is not like if it becomes 0, then there is no reason of doing anything, right? If it is okay, so let me tell you like this: 1 minus 4 determinant of J by trace of J whole square whole to the power half. Now if determinant of J is equal to 0, that means P equal to 1, that means it is fully coherent state or fully polarized light. Degree of polarization is 1. But it can be incoherent also. It can be like like for the general polarization matrix which is not fully polarized, for that it will be determinant of J always will be greater than 1, because it cannot be it cannot be other than that. If it is determinant of J is not equal to 0, that means greater than equal to 0, then only we will get P in between 0 to 1. And for a general polarization matrix which is partially coherent field, which is a partial polarized light or partial coherent field, for that it will be always in between 0 to 1. For that, determinant of J always should be greater than equal to 0. That means Jxx, Jyy minus Jxy, Jyx greater than equal to 0, or this is equal to 0. I mean, for this question you need to give the logic with this to write that determinant of J is greater than equal to 0. First, this is the first option, and there is another option with which you can do it, which is if you calculate Jxy, Jyx, then you can write it in terms of Jxx, Jyy into Jxy into Jxx, Jyy into Jyx. These are outside the root and these are inside the root. Then you can write it as Jxx, Jyy, Jxy, Jxy star. Okay, which will equal to Jxx, Jyy, Jxy squared. Now this Jxy is the polarization degree of coherence. Now that can be Jxy greater than less than 0, that can only be in between 0 to 1, which means Jxx Jyy will be greater than equal to Jxy Jyx, which again tell you determinant of j equal to greater than equal to 0. I took the help of the previous thing here to solve this problem. So this is the first thing which you can give the logic of this determinant of j equal to 0 is fully polarized. To get the generalized matrix or the partial polarized anything, that for that we need something which is not equal to 0, that means greater than or equal to 0, which will give you p in between 0 to 1, which only possible if determinant of j greater than equal to 0, or you can show it in this manner. Now the problem B is showing so that s0 square is greater than equal to s1 square plus s2 square plus s3 square. So for that you need to write the Stokes parameter, like the polarization matrix in terms of Stokes matrix. Now here I am writing for you but you please visit what is Stokes parameter and learn that. If you require help and you cannot understand, then let me know. I will next day explain to you. But for now I am considering you guys are aware about this. If you don't know, please let me know. Then only I will be able to help you. Now we know determinant of j equal to greater than equal to 0. We will use that fact which will give this. Which is greater than equal to 0, which is s0 square. If you just calculate it properly, then you will get this. I have already calculated beforehand. Please do the in between steps by yourself. So this is what is given as to proof. So this is the answer. And last but not the least, the problem is saying express the degree of polarization in terms of Stokes parameters. You need to remember this formula, the degree of polarization, which we are using several times for solving the polarization degree of freedom problems. The Stokes parameters or the Stokes variables, we can represent it in the Poincare sphere, which is nothing but just the same as what we say it as Poincare sphere or that Bloch sphere, the same thing. So it will be this. If you understand the Bloch sphere, you will understand Poincare sphere or vice versa. Okay, so this is the degree of coherence that you need to calculate, which is told here. Now there is this problem 4 which I was thinking that I will solve, but discussing that SPDC and solving this problem take many times, so I will not discuss the discuss this problem 4 anymore. That I will leave for next class. Next day I will discuss them. Discuss the whole problem, because I was just supposed to show 3 parts of this problem. There are more parts of this problem, but let's skip this. Rather just discuss the 2F imaging today, then further thing we'll discuss from the next day. So let me stop sharing this this thing and share some other thing. Stop share. I'm stopping. Stop I'm stopping the sharing of the slide and going to my code. So I have done this code in the Colab, which is a online Jupyter notebook, or Anaconda Jupyter notebook, in which we can directly use online, because I can share with you or do whatever I want to do. And so that for that reason I have done this in Colab. You can use whatever you want to do. So for that, what you need is to call the library first. I hope you guys are aware about Python very well. So we have imported the NumPy, NP, Matplotlib and SciPy package for doing the Fourier transformation. I want to show you the Fourier transformation also, because why because in this study of quantum optics, it is too much important to know about the Fourier analysis or Fourier transformation. So first what I am doing is, here I am forming the I am calling the n, which is a grid point numbers. Then a is a ACP is the separation 2, lambda is the wavelength, which is in micron. Kappa is the 1 by lambda, that is the k, that is the wave vector. And now I am generating the array x and y in the x and y, and creating a grid points in this create grids, okay, where we'll plot the object. Now we have also defined the Fourier space according to that according to the x and y ranges. And then we need to be very careful about doing the about creating the gridding point for Fourier transform plane, because because of the Nyquist-Shannon sampling theory. If you don't follow that sampling property, if you don't do the sampling properly, then you will get wrong result. So for that, you need to follow that. First I am defining this kx span, ky span, which is the 1 by delta x delta y, and then I am defining the kx ky like the Fourier transform domain, x-axis and y-axis properly, and omitting the last element just because of the Nyquist just because of the proper sampling. And then after doing all of these things, I have created a mesh grid in the xy, which is the xy basis, which xy plane, and then it's a Fourier transform basis, which is just after a lens, which will give you which is this kx grid, ky grid. Now what we need to do is that now we are plotting the f data, which is just nothing but the circular object of a radius, which is x square plus y square less than equal to a square, where a is the radius of the circle. So we are plotting, this is our object. Let me show my object. This is the object. If you plot it, then you will get this, okay. So this is the object, which is a circle, which you can see in this 2D two-dimensional flat space. Then if you do the Fourier transformation of this object, then what you will get, that I am showing in the Fourier that I am showing here. And the next plot, which is object Fourier transform, showing like this, which will be a jig function, okay. Maybe you cannot see it, but it is something like first prominent blob, then circular ring, which are not so prominent. And again, if you do the Fourier transformation, then what you will get is the image back. Now why it is 2f imaging system? Because if you have a object and then a lens, and then if you have an object, then a lens, and then if you do the imaging at focal plane of that lens, then what we will get is the Fourier transform of it, which is showing with the object Fourier transform. Now if you use again, if you do the again another Fourier transformation, that means another f system, that is becoming the 4F system. This is just the relation object and object Fourier transform. This is a relation of a 2F imaging system. Whereas if you do another F system, that is a 4F imaging system, another lens if you place, then you will get the Fourier transformation of this object Fourier transform, which is the image, which is nothing but the object itself, which we call as 4F imaging, and that is what we use in case of every imaging, even DSLR or whatever we are using, everything based on this 4F imaging. Okay, so this is just the introduction of 2F imaging and 4F imaging. You can even do the single lens imaging by placing the object and image in 4F imaging location. So single lens imaging is also possible. Just you need to be careful about the focal length, object plane and image plane. Okay, so this is the introduction of 2F imaging and 4F imaging. I tried to give you some visualization. That's why I did this simulations. Otherwise, you can also I mean, we can do something else. We can also do the Fresnel diffraction and imaging. I can tell about the Fresnel propagation, Fraunhofer propagation. All of the things are there. If you want to go much details in the optics, as well as you want to imply them in the quantum, that means quantum optics. So but yes, just to give you the flavor of 2F imaging and 4F imaging, I just did this simulation just to make you excited about this, because many people do the simulational work in the quantum optics also. So these are the stuff, and this is what I wanted to show you today. So now nothing, this is already 7 p.m. almost, and I don't want to discuss anything else. I have discussed about a lot of things today. Let me go back to my slide once again. So this is the week 7 discussion session, problem solving discussion session of Coherence and Quantum Entanglement course by NPTEL. And I discussed today about 5, 6, 7, 8, 9, 9, 10 problems in the polarization degree of freedom. And first half I discussed about some conceptual questions. If you have not listened to that part, you can go and visit to the YouTube channel uploaded video. And apart from that, I have discussed a lot of things about SPDC. I have given you the reference also, which you can visit and read by yourself. And at the last, I solve another 2 problems in the polarization degree of freedom, and then end up with the 2F imaging and 4F imaging concept with the simulation. Okay, so this is all from my side today. So let's say goodbye, and we'll start discussion on this coherence and quantum entanglement and show you some more interesting things in the week 8. So up until that time, you please revise, study well, solve these problems again and again, do the quizzes, submit it properly, prepare for the final examination, and let me say goodbye to you. Okay, so bye.